Hello again. This is Math 2232 coming to you from the College page, and the title of this lecture is More Serious Discussion. As always, please be attentive while watching this video. By way of introduction, we're going to talk about a very famous series that will become important in this lecture and even more important in future lectures. So in mathematics, the harmonic series is the infinite series given by the summation as n goes from 1 to infinity of 1 over n. So that is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus dot dot dot. And the surprising thing is that this series does diverge. Now the name called harmonic derives from the concept of overtones or harmonics in music. You see the wavelengths of the overtones of a vibrating string are, and this could be a violin string or a guitar string, are 1/2, 1/3, 1/4, etc. of the string's fundamental wavelength. So every term in the sequence after the first is the harmonic mean of the neighboring terms. And the phrase harmonic mean also derives from music. So anyway, this is the series. That's why it's called the harmonic series. Now, what we're going to do is we're going to prove that this actually does diverge. And this is a wonderful proof that came from a French monk in the 1350s. And it goes like this. So the way he proved it was to compare the harmonic series with another divergent series, where each denominator is replaced with the next largest power of 2. This is actually very clever. So here is the harmonic series: 1 plus 1/2 plus 1/3, 4th, 5th, 6th, 7th, 8th, 9 plus dot dot dot. So what he does is he says that he's going to replace this denominator of 3 with 4. And he's going to replace the denominators of 5, 6, and 7 with 8. These are the next powers of 2. And so on. And he's going to replace 9, 10, 11, 12, 13, and 14, and 15 with 1 over 16. So you see, that's what he is going to do. Now you see 1/3 is greater than 1/4, and these guys are greater than 1/8, and so on. And so he does have this inequality. So the harmonic series is greater than all of these. But now what he is going to do, he's going to group these terms that he's getting this way. So he just leaves 1 alone, and 1/2 is 1/2. Then he takes the 2 1/4ths, and he gets 1/4 plus 1/4. He takes the 4 1/8ths, and he gets those that will add up to 1/2. And he will take the 8 6 1 over 16s, and that will add up to 1/2 plus, and he can keep on doing this forever because you never run out of numbers. So that means, and that's dot dot dot, so that means that this is equal to 1 plus 1/2 plus another 1/2 plus another 1/2 plus another 1/2, and you can keep on going and get as many halves as you want. And so you see, that means that when you add up all these halves, it's going to be bigger than any number. It's going to be infinity. And here infinity is a notation indicating that partial sums grow without bound. And we talked about what bound meant, so this grows without bounds. So it follows then that this thing that we started out is bigger than or equal to, and notice that they are careful here. You have to sum from n equal 1 to 2 to the k of these, but then that means you'll have k of these things that are equal to 1/2. So this sum is bigger than 1 plus k over 2 for every positive integer k. But that means I could take k to be a billion, k to be a trillion, k to be a googolplex, which is actually of a number, a very large number. So you see, this gets bigger and bigger and bigger. Now, this is both surprising, because who would have thought that this wouldn't converge? And it's also important as a comparison test and other things. So this will be very important. So I'm asking you to keep this in mind from here on out. This proof again was by this guy, and it was back in the 1350. That was AD, and this is a very pretty proof. And this is what I teach. Now there is another test that we may reference later, which is called Cauchy's condensation test, and that's a generalization of this argument. This is some very pretty mathematics that I just showed you. So the harmonic series surprisingly diverges. As I was looking over this lecture, I decided to add this slide because the notes just pull this kind of out of the air, which you kind of say, well, where the heck did this come from? And so I am explaining it. And what is asserted later is that if you add up the numbers 1 plus 2 plus 3 plus 4 dot 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 all the way up to n, that this is exactly equal to n times n plus 1 over 2. Now you did learn this in your Calculus 1 if you studied Riemann sums, but you might not remember that, so I thought I'd just show you a proof of that here. And this is a very slick proof as well. So s is equal to 1 plus 2 all the way up to n, but then s is also equal to the same thing if I add it backwards. But now I'm going to add it up and down. So if I add it up and down, what will happen is we'll get s and s is 2s. I'll add the blues and I get n plus 1. The greens I get n plus 1. The yellows I get n plus 1. The reds I get n plus 1. These reds I get n plus 1. Yellows, greens, and blues. I always get n plus 1. And how many of them are there? Well, there are n of them. And you could count them just up here. So there are n of those. So that means that 2n is equal to n times n plus 1. And that means that the sum that we originally talked about is n times n plus 1 over 2. This is very slick, but later on we'll encounter this and I'll just say, oh, we've already talked about that. Let's dive back in to what we want to be talking about though, and that's the series. So I'm reminding you that we started with a sequence, a sub n, where n equal 1 to infinity, but then we're going to form another sequence of partial sums. S1, S2, S3, S4, all the way down to S sub n, and S sub n is equal to the summation of the a sub i's as I runs from 1 to n, and these form another sequence that looks like this. This is S sub n going from 1 to infinity, and this is pretty much what we covered last time, but the sum of these is the limit. As n goes to infinity of s sub n is the sum, and we write it this way, the summation from I equal 1 to infinity a sub I. And it's important to remember that this is really nothing more than a convenient notation for this limit, and we don't keep writing the limit down, but we always need to remind ourselves that this limit is here. Okay, now if the sequence of partial sums is a convergent sequence, and you see you've got the sums and the sequences that are interplaying here, you need to keep that straight. But if the sequence of the partial sums is a convergent sequence, that means the limit exists and is finite, then the series is called convergent. And in this case, limit of s sub n is equal to s, and then the summation from 1 to infinity of the a sub i's is also equal to s. Likewise, if the sequence of partial sums is a divergent sequence, that means its limit doesn't exist or is plus or minus infinity, then it is called divergent. So again, the words convergent and divergent apply here as well. Okay, so here's an example, and again, you should be familiar with this example. So here the example is you want to determine if the following series is convergent or divergent, and if it converges, determine its value. So this is a summation n going from 1 to n of n. Okay, so this would be 1 plus 2 plus 3 plus 4 dot 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 and keeping on going. Now to determine if the series is convergent, we first need to get our hands on a formula for the general term in the sequence of partial sums. So S sub n is equal to the summation I equal 1 to n of I. Now, this is a known series, and its value can be shown to be this. And I already showed you that this is true. So S sub n is equal to n times n plus 1 over 2. Now that is a formula that is known, and I showed you a proof of that. So now what we can do is we can say, okay, what happens as n goes to infinity of this sequence? So this is the sequence of n times n plus 1 over 2, n going from 1 to infinity. Does that converge or diverge? Well, this clearly gets as big as you want, and so this diverges. And so what we see is this series diverges. Okay, now as we saw in this example, we had to know a fairly obscure formula to determine the convergence of this series. But in general, finding a formula for the nth term of a partial sum can be a very difficult process. In fact, we're going to be doing much more powerful tests as we go forward, and so we won't always have to face this extreme difficulty of finding this general formula. And that also means that we're not going to be doing as much work with the value of the series, since in order to get the value, we need to know the general form. So anyway, we'll have some more examples, and will also lead us to, these examples will lead us to some very important facts about the convergence or divergence of series. So please stay tuned. Here's another example. So here we want to determine if the following series converges or diverges. If it converges, determine its sum. So this is a summation from n equal 2. N can't equal 1 or you'd have 0 in the denominator. So from n equal 2 to infinity of 1 over n squared minus 1. And again, this is a pretty common statement of the problems I might ask you to do something. Now, this is a technique that we're going to talk about a little bit more later, but actually we're going to solve this later using a different technique. But this is one of the few series which we can actually determine a form, and here's the general form for this. So if you take the summation from I equal 2 to n of 1 over I squared minus 1, you're going to get 3 over 4 minus 1 over 2n minus 1 over 2 n plus 1. Now this is even a more obscure formula, and I'm going to show you an easier way to do this problem later. But for now we have this formula, and you should take it this as a given. So in this case we have the limit as n goes to infinity of S sub n is the limit as n goes to infinity of this formula. Now this thing will go to 0 because of the n in the denominator, and this thing will go to 0 because of the n in the denominator. So this thing really adds up to 3 over 4. So this is another problem that we have solved. Here's another example. Determine the following series converges or diverges. If it converges, determine its sum. If it diverges, I want you to explain to me why it diverges. Okay, in this case, we really don't need a general formula because we can look and see that S0 is going to be 1 because minus 1 to the 0 power is 1. But then the next one, S1 is going to be 1 minus 1, which is 0. Then S1 is going to be adding 1 and back again. So you see this is going to bounce back and forth between 0 and 1. So the sequence of the partial sums looks like this sequence. It is 1, 0, 1, 0, 1, 0, 1, 0, dot, 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 dot. And so that means that this never gets close to a real number and stays close to a real number. So therefore, since this doesn't converge, this sequence, it diverges, and that means that this limit doesn't exist, and that means the series also diverges. Let's check another one. Here's example 4. Determine if the following series converges or diverges. If converges, determine its sum. So this is a summation from 1 to n of 1 over 3 to the n minus 1. So this is 1 plus a third plus 1 over 9 plus 1 over 27 plus 1 over 81 plus dot, dot, dot. Now, here is a general form for this. Again, this is clever, and we'll see an easier way, at least for this problem. So what we're going to do is we're going to factor out 3 over 2 out of this. And when you factor out 3 over 2 out of this sum, you get 1 minus 1 over 3 to the n. Now, again, this is clever, and just take this as a given right now. But what now will happen is we're going to take the limit as n goes to infinity of this partial sum. Well, when we take the limit as n goes to infinity, the 3/2 just sit there, and this thing right here goes to 0, making what's inside the parentheses 1, so this is 3 over 2. So this sums to 3 over 2. So what's the takeaway from these 4 examples? And you may guess this, you may not, but this one diverged, this one converged, this one diverged, this one's converged. So note that, or notice that for the 2 series that converged, the series term itself was 0 in the limit. As n goes to infinity, this is 0. As n goes to infinity, this is 0. And so what that means is that there's potentially a theorem here. And in fact, this is always going to be true for convergent series and leads to the following theorem. And the theorem says if the summation of a sub n converges, then the limit as n goes to infinity of the nth term is equal to 0. Now here's a proof of that. So suppose that the series starts at 1. Then we have Sn minus 1 is equal to this sum. And writing it out, I get this. And S sub n is this. So that means if we subtract Sn minus Sn minus 1, we get A sub n. But we know that this is convergent by our if part. So if this is convergent, we know that this sequence gets closer and closer to S. So as n goes to infinity, it becomes S, so it is a number. So that means the limit as n goes to infinity of an, written this way, is the limit as n goes to infinity of Sn minus Sn minus 1. So these are both, you can distribute the limits there. So this is going to be S minus S is 0, and we've proven this theorem. So if this converges, then this limit is equal to 0. But please be careful not to misuse this theorem. Many of my students do. This theorem gives us a requirement for the convergence, but not a guarantee of the convergence. It says if it converges, then this goes to 0. But we can look at this, which is the harmonic series, and you see 1 over n also goes to 0. But this diverges. And later on, we're going to see that this one converges. We haven't shown that yet. But you see, so the limit as n goes to infinity of a sub n equaling 0 does not guarantee convergence. You want to think about that for a while. Okay, if I guess this just talked about that, but this is actually, when I look at the contrapositive of this, so that was if P then Q, this is if not Q then not P, is actually a very important and useful test. And I will tell you, this is the first thing that I think about in every series problem that I look at, is I say, oh, how does it work for the divergence thing? So what we showed is, if the summation a sub n converges, then the limit is equal to 0. So the contrapositive is, if the limit as n goes to infinity of a sub n does not equal to 0, then this will diverge. This is a very quick and very powerful test. Again, do not misuse this test. This test only says that a series is guaranteed to diverge if the terms don't go to 0 in the limit. But again, we have the fact that this diverges even though they do go to, and this is going to be proven later that this converges. This will be converging to pi squared over 6, and we'll do that later in this course. So one of the more common mistakes that students often make when they first get into series, and that's what many of you are doing right now, is to assume that if this limit as n goes to infinity of a sub n is equal to 0, then this will converge. There's no guarantee of this. So be careful and make sure you understand this discussion, because this is our first convergence or divergence test. Here's example 5. Let's look at this. So we're to determine if the following series is convergent or divergent. Well, you see, if I look at the nth term here, I have minus n cubed in the numerator and I have 2 n cubed in the denominator. Those are the highest order terms. So I know that the sequence of the a sub n's is the ratio of those terms. So it's going to be minus 1 over 2 or minus 1/2. So the limit as n goes to infinity of a sub n is minus 1/2. That's not equal to 0. Since that's not equal to 0, that means that by the divergence test, the series diverges. Make sure you follow this. Okay, now the divergence test is the first of many tests that we're going to be looking at over the balance of this course, and you need to keep track of them and the conditions that must be there for them to apply, because these will be kind of essay questions on a test, perhaps. Okay, and we're reviewing the arithmetic of the series. I think we've really already talked about that. If you have c times a sub n, you can pull that out. And if you have the summation of a sub n plus or minus b sub n, you can break it out like this. Now, we need to be a little careful about these facts when it comes to divergent series. However, we were saying, oh, if both of them are convergent, this are true. If they're divergent, if the summation of Cn is divergent, then so is the summation Can will also be divergent, provided the C's are not equal to 0. Since multiplying a series that is infinite in value or doesn't have a value by a finite value won't change the fact that it has an infinite value or no value. I don't know if I like that sentence, but I think you'll understand that. However, it is possible for this and this to be divergent series, but if you add them together, you get a convergent series. And we can look at examples of that. In fact, I expect you could come up with your own examples of that. Now, more discussion. Since the main topic of this section is the convergence of a series, we should mention a stronger type of convergence. A series, summation a sub n, is said to converge absolutely if the summation of the a sub n's also converges. This is the absolute value of the a sub n's. Absolute convergence is stronger than convergence, than regular convergence, in the sense that a series that is absolutely convergent will also be convergent, but a series that is convergent may or may not be absolutely convergent. In fact, if a summation a sub n converges and the summation of the absolute value of a sub n diverges, then the series is certainly not absolutely convergent, but in fact we have a word for this. It is called conditionally convergent. This is a much weaker form of convergence than absolute convergence. Now at this point we really don't have the tools to properly investigate this topic, but we will soon. Okay, so we're not going to say much more about this, but we are going to do another very amazing example. In the previous section, after we started talking about infinite series, we commented that we shouldn't think of this as an infinite sum, despite the fact that the notation we use seemed to imply it is an infinite sum. Now is the time for us to discuss this. And this is pretty amazing, so hold on to your hats. First, we need to introduce the idea of a rearrangement. A rearrangement of a series is exactly what it might sound like. It's the same series with the terms rearranged in a different order. For example, if we had this summation in from 1 to infinity of a sub n, this is a1, a2, a3, a4, a5, a6, a7, plus dot, dot, dot. If we shuffle these terms, keeping the same ones, but we have A2, A1, A3, A14, A5, A9, A4 plus dot dot dot, some other shuffling. That's a rearrangement of the series. Now, the amazing fact is that for some series, and these are series that are conditionally convergent, each of these rearrangements of terms can have different values. And you might say, what? Well, I'm going to show you an example of this. Now, it can be shown that the summation n equal 1 to infinity of minus 1 to the n plus 1 over n, which is known as the alternating harmonic series, and that would be 1 minus a half plus a third minus a fourth plus 1 over 5 minus 1 over 6 plus 1 over 7 minus 1 over 8 plus dot 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 is equal to the natural logarithm of 2. We will show you that in this course later. Now, since the series does converge, I just told you it did, and I will show you that later, we know that we can multiply it by a constant, so we're multiplying by a half. So if we multiply all of these numbers here by a half, I'll get 1/2 minus a fourth plus 1/6 minus 1/8, so on and so forth. That is equal to 1/2 of the natural logarithm of 2. But now we're going to add a 0 in between each of these terms. And so what we're going to do is we're going to add this side to this side. But we're adding them up and down like we did. So you see we're going to get 1/2, and then we'll have 1/2 minus 1/4, which gives you it gives you these things in a different order. So we're adding up and down. And so what we will get is that this will be ln of 2, but this will be 2 ln of 2. So you see, we're really, we made this sum turn out to be something different because we can rearrange the groupings, and I was grouping it this way. So that's kind of an amazing fact, and in fact, this is a famous piece of mathematics called Riemann's rearrangement theorem. Now, that is really amazing. In fact, here are the facts that you need to know. And facts really are other words for theorems. So given a series, the summation of A sub n, if the summation of A sub n is absolutely convergent, its value under any rearrangement will also have a value of S. It doesn't change if you rearrange the term. But if the summation of A sub n is conditionally convergent and R is any real number, then you can rearrange this to get that value of R. You can rearrange it to get any value you want. Now, this is an amazing thing. We'll talk more about absolute convergence later on, but you want to walk away knowing, wow, this is an amazing thing, and conditionally convergent series are very fragile things, and absolute convergence is a strong form of convergence. As a final note, the fact above tells us that this must be conditionally convergent. This is the alternating harmonic series because we showed that you could rearrange it and get different values. So this is conditionally convergent. It's not absolutely convergent though, because think, if you took the absolute values here, you would get the harmonic series, which is known to diverge. This was a pretty deep lecture, I think. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.